All right, let's get started. Welcome everyone to second number theory week as part of the math and machine learning program here at CMSA. I know several of you were here for before, but I see a bunch of new faces as well. So I thought maybe we should just start by going around the room and quickly introducing ourselves. I'm Andrew Sutherland. I'm a computational number theorist at MIT. Thank you.
Other question? This number is MIT.
Or maybe Michael. Yes.
I'm Mike Douglas. I'm here at CMSA. I'm a physicist by training, but it was not.
I'm Vasily Krylov. I'm a new author at CMSA Harvard. Yeah, I'm doing geometric representation theory with years.
I am Kit. I'm a rigorous mathematician and I'm interested in machine learning, maths, and physics.
Yeah, I'm Thomas Harvey. I'm a lifeline at MIT. I mostly work on applications of machine learning methods to string theory and related parts of geometry.
And around different number theory.
Burin evaluate number theory, BU postdoc.
I'm David Larry Doolan. I do computational analytic number theory at ISTARM and Brown.
I'm Jennifer Balakrishnan at Boston University.
Hi, I'm Kate Finnerty. I do number theory. I'm a grad student with Jen at Boston University.
I'm Kyuhan Lee from University of Connecticut. I'm interested in application of AI to pure mathematics.
Hi, I'm Melanie Medjwood. I study number theory and professor at Harvard.
I'm Arul Shankar. I'm a number theorist at the University of Toronto.
I'm Georgi Pai, studying applications of machine learning and studying string theory.
I'm Tomás Silva from University of Campinas, Brazil, and studying applications of artificial intelligence to the great geometry.
Hi, I'm Ken Thompson. I'm a physics professor at Northeastern, and I work on string theory and machine.
Hi, Joanna Barbarian.
I am from Temple University. I studied Gauss representation and also did a bunch of machine learning stuff on the side.
I'm Padma. I'm at Boston University. I do everything.
Hi, I'm Fabian. I'm at Northeastern University, and I'm also string theorist by training, but I work on multiplying reinforcement problems.
Some new just walked in.
Yeah, hi, I'm Takredi. I'm from Mary in London, and I do some machine learning applied to string theory, differential geometry, and algebraic.
And is there anyone on Zoom who wants to introduce themselves? Yeah, please go ahead, Jim.
Yeah, hi, I'm Gergely Berti from Aarhus University in Denmark, and I'm an algebraic geometer and have just recent work in machine learning applied to geometry and some combinatorics problems.
Ash?
I'm Ash, and I'm a number theorist at BU. And I'm interested in learning this week.
You're going to do a pretty strong speaker.
Yeah, thank you. All right.
That's strong speaker.
Yeah, no, it's not.
Okay, I think
I'm sorry. Yeah.
Great. I'm thrilled to have such a large group and a diverse group here. I was worried it would all be number theorists, and it's not. That's a great sign. Especially for this week, because in the first week on number theory, we mostly look at more traditional machine learning data science techniques, analyzing large data sets, looking for patterns. And if there are those of you who were here in the first week and are just itching to continue something you're working on during the first week, that's fine. But I also want to invite you to think about some new approaches, which is really going to be the focus of the second week. So what I'd like to do, what I'm hoping to accomplish in this week, is to get people thinking creatively about ways to use some of the really recent new tools in machine learning that are now available, specifically transformers and the large language models, several of which are now available for quite reasonable costs that will try to figure out ways to apply these new tools to solve problems in number theory. But I think to some extent, a lot of the work we do this week is not going to be at all specific to number theory. It's going to be more about trying to think about a bit creatively about how we can use large language models to solve problems in mathematics. Now, to sort of get people started thinking about these, and I want to just I'm going to spend like 10 minutes talking, and then we're going to turn over to a demo, and then we're going to start brainstorming projects. But I just want to get people's juices flowing a little bit.
Should we do the brainstorming process before the demo? Just.
Yeah, you want to do the brainstorm? Okay, yeah.
Because otherwise we're gonna can people like how to use the tool.
Yeah, fair enough. Okay, so there may be like 3 or 4 different things I wanted to, that were thoughts that I had in my mind, but it might even be worth polling the audience, especially because we have people in the room who know a lot more about machine learning than I do. But sort of the things, actually, before I do that, is there anybody here who is not on the Math ML 2024 Zulip? There is, please send me an email, drew@math.mit.edu, or send Mike, and we will get you on the Zulip, because everything's gonna happen on the Zulip. I've already posted a bunch of links there, and I'm gonna keep posting links there. So that's the place to stay up to date with everything that's going on, especially for people who are participating remotely. Okay, so the sort of 2 immediate things where I think we can build on work that's already been done as part of this program is Francois Charton created a package which you can now download from GitHub called Int2Int, which will is a transformer-based application for building small models, but models that are big enough to do some interesting things. And it has a very simple interface. You're basically trying to teach it to translate one sequence of integers into another sequence of integers. This is sort of like the canonical kind of task that you might think a large language model or transformer ought to be good at. And so we've had a few experiments around this already. Edgar is maybe going to say Edgar is going to give us a demo on how to use int-to-int. And they had some good success on using this to solve at least one of the problems that we came up in the first number theory week, which was trying to understand failures of local to global principle for torsion on Jacobians of genus 2 curves. But I think that the specific example is probably less important than understanding how to use the tool. One thing, someone should correct me if I'm wrong, but as far as I'm aware, all of the experiments that have been done using int2int, at least in the number theory group, have mostly been having the output sequence be just a 0 or a 1. And I think it would be much more interesting to try to think about problems where it would actually be really doing a translation rather than just doing a classification problem. It's kind of a miracle that it actually seems to do quite well at classification. So even when the output is just 1 bit, it's able to learn some very nonlinear functions. So that's a good sign. But it would be, I think, really intriguing. I'm sure it would make Francois very happy if somebody were to find a neat way to utilize this tool to actually learn a translation problem that has relevance to the mathematics that you know about. And it's easy to use. It's just, you can load it up in Python. I also wanted to mention we've set up, so in the first week we had a CoCalc server, which also you can just run as a Jupyter Hub server if you're more familiar with Jupyter interface. We've changed the configuration of that server for this week and now has 8 GPUs attached to it. They're not huge GPUs, they're L4s, but I think they're big enough for the kinds of things, the experiments that we might want to run this week. But that means you can run int-to-int experiments much more quickly than you could if you were running it on a compute-only instance, and you're not necessarily obliged to run it on your own laptop. I'm not going to assume that everybody has a GPU on hand. So I think 8 should be more than enough to keep us busy, but happy to try and spin up additional resources if we need them. Okay, so that was int-to-int. So int-to-int, the idea is we're actually trying to train a new model on some, not billions of parameters, but maybe millions of parameters in that kind of range. And I think on focused problems, that approach, at least in many other domains, has proven to be successful. And I think Francois is a fan of that approach. And so I think that's one avenue that I'd really like to see some subset of us pursue this week. The other, or another approach that might be worth considering that we at least have made, I think, some significant progress on last week in particular, is trying to adapt the Google DeepMind's Fun Search package which was used, for those who aren't familiar with it, Jordan Ellenberg and a number of theorists collaborated with some engineers at Google DeepMind, and they were, in a nutshell, using a large language model as a sort of black box to drive a genetic algorithm running a heuristic search. And the heuristic search they were using was they were looking for larger, what are called cap sets. So this is in the vector space, F3 to the n, you want to find the largest number of points such that you don't have, that there's no line, that they're not collinear. And the approach that they took, I think if we as mathematicians, we might initially think about the structure of the problem. Oh, we're gonna show the large language model a whole bunch of vectors in F3 to the n, and it's gonna learn what makes those vectors good, and then it's gonna somehow generate or show its subsets of these vectors, and it's gonna come up with a new better subset. But that's not at all what they did. What they did instead was they used the large language model to generate Python programs that are good at generating large cap sets. And when I say generating, that's really an exaggeration. The way the fun search model works is there's basically two functions. There's an evaluator, which tells you how big the cap set is. It tells you this is what you use to measure the fitness of a sample in your population. And then the programs themselves that they were generating were not actually generating cap sets. They only have to do one thing, which is assign a priority to rank, to order the vectors in F3 to the n. That's their only job. And the input is, here's a vector, tell me its ranking or tell me its priority. It basically is assigning a real number to a vector. And then there's a skeleton around it that is basically take the highest ranked vector, put that in a cap set, take the next highest ranked vector that actually doesn't violate the cap set position and put that in, and keep going until you can't go any further. And that, you call that the cap set output by this program. Now, I think that I'm glossing over a lot of details. I encourage you to read the DeepMind paper, which is quite short, by the way. Don't be afraid. I mean, if anything is too short, they don't explain all the details. But I just wanted to make sort of two comments. First, if you're interested in the details, the good news is that Kit has a complete implementation of parallel now, I understand, of the fun search infrastructure. But instead of using the Gemini large language model that DeepMind is using, where it's set up so you can use Mistral, which is we have a certain number of credits. But there's no reason it's specific to using the Mistral large language model. You could plug in I don't think it would take much tweaking to use a different one. So we have set up on our CodeHouse server, we have access, we've set things up so that we can people can use the Gemini API, but we're also going to set it up. We haven't installed SDKs yet, but we will today, so that if you wanted to play with Anthropic's Collect 3.5 Sonnet or any of their models, or also OpenAI, the ChatGPT 4o Mini or any of the other ChatGPT models. I think for running small experiments, these APIs are very inexpensive. I mean, the costs are measured in a few dollars per million tokens. And if you're just experimenting, just trying to see if you can get a framework working, you're going to have a hard time actually generating a million tokens. So I've generated a bunch of API keys, which with a very small amount of money put on them, like $20, but I think that's enough to run some experiments. So if there's anybody who's interested in using those, I'm not going to post them publicly on Zulip, but I'm happy to message them to you privately and go to town. We also have a much larger budget potentially available for credits on Mistral AI, so there is some advantage there to experimenting with that API, just because we could run some larger experiments, although I think we want to be a little bit judicious about which experiments we choose to run. I also have, independent of Mistral, I also have access to some Gemini credits, which I would also be happy to spend if somebody comes up with a promising project that uses the Gemini API. Okay, so just a few comments I wanted to make about Fun Search is, in some sense, it's a very constrained. They picked it was key to them to find a structure, a very sort of narrow, tight structure into which they could, cram their problem into, which is, we're just gonna iterate over a population of Python programs whose sole job is to take a vector in F3n and output a number. They weren't specific to CAPSA. They also give a bin packing problem, but they're all using the same infrastructure. But I think the intuition behind it is LLMs that have been trained on, the vast, almost the entirety of the internet, probably don't actually know that much math. They probably don't know very much about the CAPSET problem in particular, but they know a whole lot about Python programming because they've seen tons of it in their training set. And so coming up with a way to structure the problem so that you're taking advantage of sort of this native ability, this LLM knows how to write Python code, and even better, it knows how to take 2 Python programs or 10 Python programs and generate another Python program that's kind of like those, but not exactly the same. That's exactly the sort of the key ingredient to a genetic algorithm. The other things, independent of AI, I'm also a fan of genetic algorithms. We use these very successfully in the Polymath project on prime gaps. This was back in 2014 when GPT-2 was still a twinkle in somebody's eye. And so we weren't using machine learning at all, but we were using an algorithm this was a program to find narrow admissible tuples where we would take admissible tuples, these are sequences of 1s and 0s whose offsets indicate a sequence that could conceivably, if you shifted it, be populated by prime numbers. So for example, you can't have a sequence of prime numbers where 2 of them differ by a multiple of 3, or where 2 of them are even, or where 2 of them differ by a multiple of 5 because they can't both be prime. And so there's a way to combine these admissible tuples and then generate and then trim them to make them admissible again, and this sort of leads to a natural idea of a genetic algorithm. But there was no Python code involved in that. We were actually, the phenotype and the genotype were literally the sequence of tuples that we were iterating over. But I think it would be a worthwhile exercise for some people to think about this week would be, are there problems, heuristic optimization problems that we care about that might be suitable for a genetic algorithm programming approach? And is there a good way to translate that problem into a form where it can be implemented by having a large language model, combining Python programs? So somehow you want to encode your problem in a way that where the genotype, if you will, is something that the large language model can operate on efficiently and intelligently. But the phenotype is up to us. We can have we can turn whatever the output of the Python program is into whatever mathematical object we can run. So I'll post, so there's, Kit has set up a GitHub repo with excellent documentation on how to use the package that he's created that sort of that implements the fun search. There's also Google DeepMind posted a GitHub repo of their own, but I think I would encourage you to go to Kit's repo because he sort of filled in all the missing pieces that weren't completely explained in the original application. Okay, so those are sort of 2 very concrete things to play with, would be intent and fun search. And we have existing GitHub repos, and there are links on the Zulip to them if you want to download them and play them, and you can load them up in a Jupyter notebook on the Cohout server that we've set up and try them out. But I also wanted to think, stepping back a bit further, I think the fun search is one sort of very specific way to channel the idea of let's use a large language model's ability to iterate over Python programs. There's probably lots of other ways to do that. So I don't think we should lock ourselves in necessarily to the fun search model. I think there are also other capabilities of LLMs, especially commercial LLMs that are now available that aren't really being exploited necessarily in the fun search model. So if you go on to Anthropic or OpenAI, or I haven't actually used Mistral, but I'm sure it's similar. When you sign up for their API, in addition to getting a token you can use to make API calls, you also have the opportunity to decide what the system prompt should be. I mean, this is basically OpenAI advertises these customized GPTs you can create, where you're basically just tweaking the system prompt. But this sort of lets you tell the LLM how you want it to behave, what its output should be like, what it's trying to do. This is probably not going to help much in the details of the problem, but it might help in terms of the structure. But the second thing you can do, which I think is potentially more interesting, is exploit the context window. And some of these APIs, especially Gemini, have very large context windows. So you can load up megabytes worth of information into the context window that's sort of augmenting the training data, the data that the LLM has already been trained on, and will direct its attention on, yes, I know you've been trained on the entire internet, but here's the very tiny subset of it that I think you should really focus on before you start trying to answer any of the questions someone asks you. So I think this could also be, I'm not aware, hopefully someone will correct me if I'm wrong, but I'm not aware of anyone exploiting this idea in the context of mathematics. Most often it's used by, corporations or law firms that are wanting the LLM to be familiar with all their specific policies or handbooks or, user guides. But there's no reason why we can't use the context window for other purposes. Okay, I think I have talked long enough. Are there any questions or suggestions? Things I didn't think of that we should try?
How central is it that the outputs have Python strings or Python frameworks? Like why focus on that? And
I have no.
As opposed to a different language.
So I have some projects in mind where like if they could create like a magma script to compute something.
Well, its performance is kind of proportional to how much training. So Python is asking for training.
Yeah, it'd probably be 10,000 times better at writing Python.
So that is Python is very central.
I think JavaScript would probably work pretty well. I'm not sure that's a good alternative, but yeah, I mean, I think that the metric is not the programming language. The metric is how much of it has the LLM seen. You're trying to find, you want to try to exploit, it's like you've got a star athlete, but they're really good at one particular thing. You want to slot them into your team where you can take advantage of their capabilities and don't try to ask them to do something they've never had any practice.
And on that note, like, even if you assumedly we could speak malware, if you've never seen that thing before, never going to recreate it. So even the Python scripts are going to be very simple. If you ask for something very advanced that only saw like a few times, it's very hard to recreate it again.
I think another reason Python is a good choice is just that it's untyped. It's not strongly typed. It's very flexible, which makes it easy to make things that would break a stricter programming language will actually still produce Python programs that run. Other questions or suggestions? Has anybody tried any of it other than Kit? Has anybody tried any of the things that I'm? Well, Angie has, yeah, I should have mentioned, and we're gonna get a demo tomorrow. Where Angie is going to show us how to use the Gemini API. And she's going to demonstrate some of the work that she's done on a project that we ran over the summer, where they were trying to optimize Mestre-McGow sums or similar quantities that are used to search, heuristic tools that are used to search for large rank elliptic curves. But I think this idea fits into another category of problems. I posted a few of them on the Zulip. One of them was suggested by Terry Tao on trying to use, there are a lot of situations I think in math in general, but specifically in number theory, where we have some strategy for proving a theorem that depends on a lot of parameters that we would like to optimize. And we often don't have any clue what the right way to optimize those parameters is. This was very true in the polymath project, where there were like 3 different teams whose job was solely amounted to trying to find different combinations of parameters, and often there's too many to do an exhaustive search through the space, so you have to resort to a heuristic search. But you don't really care about where the parameter choices come from. At the end of the day, you're going to get a rigorous theorem no matter what parameters you put in there. It's just a question of the better the parameters are, the stronger your result is. So this was, I think, I'll invite you to read Terry's blog post, but this was the intuition behind this exponent database that they're trying to build, that we should feel free to use any and all tools, including black box LLMs that we may not even understand how they're arriving at their recommendations, but if they can give us good recommendations, we can get better theorems. And this idea of trying to optimize parameters in a large but not ridiculously large dimensional space is one that I think might be worth pursuing. I think there are other problems that, and there's a lot of situations in analytic number theory in particular where the name of the game is just coming up with the right test function or the right combination of weights. Anything you can do to improve those by hook or crook is going to give you a win. You might be able to improve the best known bounds for various. Yeah, Melanie.
Are we going to hear, I don't know if this is part of the next presentation, a little bit more about the use of end-to-end to find these local global failures?
Are we?
No.
Okay, could you say it in a few more sentences? So I played with end-to-end And I mean, it was sort of cool to see how it could do some, you know, basic, I played with it more like iterating around, you know, Francois was starting with GCD and modular arithmetic and around that, and it was like, that felt like it was at the boundary of what it could do, though of course, we don't need end-to-end to compute GCD for us. I understand that point, and I really like your point about the sports analogy, like we should use the player for the skills that they have and not for anything, but given my sense of it after playing with it, I'm really curious to hear like what kind of thing it was computing for in the failure of local to global. What was the nature of the?
I spent 0 time looking at the inside of it.
Okay, but what was the?
But you got fairly good results. Did you ever determine whether it was overfitting?
It wasn't overfitting because the program crashed before that.
Okay, so what was like the input? Some like.
Why don't you explain the experiment? Don't try to explain what it's.
Like what was the coordinates of something, and then it tells you if there's a failure of local to global, or?
Can I look at what I wrote?
Yeah.
I honestly like this was we did this.
But I think it did better than linear regression. I mean, it did better than some of the more standard. I think the basic idea was it was being fed APs and possibly AP squareds for a bunch of small primes for a large data set of genus 2 curves. Where we had computed the global torsion and then the GCD of all the local torsion everywhere. And then we computed an index, which was, you know, we knew how far the global torsion was below the GCD of the local torsion. And I think we were probably doing this across isogeny classes of Jacobians. And so the interesting thing here is, you know, this is just number theory, not machine learning. In theory, this shouldn't work because if you have torsion locally everywhere, and abelian surface with torsion locally everywhere should be isogenousous to the abelian, not should be, is known to be isogenousous to the abelian surface with global torsion. However, if you restrict to principally polarized abelian bodies, in particular Jacobians, that's not true. So the local to global principle for torsion can fail even at the level of isogeny. So the input sequence was for each isogeny class of Jacobians of genus 2 curves over Q, we gave it a bunch, Edgar gave it, and Jen, I don't know who else was working on this project, gave it a bunch of data.
Yeah, we gave it just APs and AP squares.
As what? Because, I mean, it doesn't.
As integers, arrays, or like we did.
Like in their like decimal representation or something, because it doesn't take ins, right? It's just sort of.
It's like some base, as decimal representation.
Okay, so you.
So we give it like first 100 APs and AP squares, let's call that. That's the, I think we're like, you know, A2, A4, and then A3 and A9 and so on and so on. And then the thing to guess.
With several place values of it.
So the input is like APs and AP squares, 100 of them, and the output was local to global failure there's a whole or not. No, but so and I don't like to say these things, especially like where the good score, like it could guess, I think, about 90% of the time. I remember that class on the logs, which was surprising because the data was already skewed, but not that skewed. So that was surprising, managed to guess anything. But now the honest part, this happened like as I was flying somewhere. So I let the experiment run. We saw the results, and I never thought about that anymore. But the key thing is that I don't really want to learn what is really thinking behind the scenes. I want to see like if I give less APs, let's give the same result. If I give more APs, it's the same result. If I take the easy cases, there's the same thing. That's the point. I don't think it's doing anything magical, but I've not done it yet. So be clear, I've not put any effort to try to figure out what are the key parameters.
Is there a problem? I don't know the problem. Is it a problem where, you know, in principle, there's some algorithm?
No, that's the issue. There's no in principle there's no algorithm. But
because it's also interesting to take problems where it is now.
Actually, there is in
okay, principle. So there's in principle,
there
sure.
Is in principle. Did you enough APs and AP squares? You could compute the model representation for a bunch of small. I mean, you could compute the image of Galois and figure it out, but that's hopelessly impractical, even for a human, never mind the large language models that's already embedding everything.
I guess one thing that I'm curious about is if the end-to-end was actually outperforming a neural net that would have just interpreted those numbers already as floats.
So I think we did some experiments with that because, yeah, I think we tried to run some easy neural networks.
Yeah, I was trying that and nothing got near the accuracy that it did.
Yeah, do you understand my point? He was like, end-to-end doesn't, when you give it those digits, it doesn't know that it should like multiply them by powers of your base and add them together. It has to learn that.
Yes.
So it's very interesting if.
Again, I do not know exactly.
And we expect that's largely what matters, the Archimedean size of the APs, or?
I think so. I think it's very arithmetic. I mean, what would, like as a human, if I were looking at it and I noticed, oh wait, I don't see any APs that are congruent to, all the APs are divisible by 3. Or I see some traces are missing from some of the APs, not every residue class is hit. But I think with 100 of them, it would be very hard. I mean, I'm sure that Intuit is doing better than I could. Just looking at
So
it.
you think that there's some arithmetic.
But there is another baseline, which is to do the same kind of tokenization. It's the same, that to a standard.
I think we're trying to put a purpose on int-to-int. And I think this was a single experiment.
Yeah.
With no further insights. So I think the first thing to do is to do more experiments and figure out what has happened. And again, I'm going to say again, the only thing I did was, I don't remember where I was. I downloaded the logs, I put the logs, and I was like, I'm off.
It's yes, and I will testify, it's very easy to jump in and use it, so.
Yeah, good.
Yeah, respect to generating this experiment, is that did you just put APs in, or did you use some sort of encoding of the APs?
So we need to encode in some base, and that's part of the thing. But for these guys, the APs are so small that I think the base work was 10,000. So I'm sure that each encoding of AP is just one single token and the sign. So that's
they're small integers.
So do you imagine that if you change the method of encoding, would that matter?
Sure, I'm sure that matters, at least for the GCD thing, for example, I think in some ways, to understand it, one should look at this basic example of pipeline GCD or multiplication model or some number. The base plays a big role. Like it's I don't remember what was the default thing, mod 62. So first it learns very well to detect factors of 2 and so on. So it's very, I think the base plays a big role. So in this case, maybe we're lucky that the APs fit in one token, so there's now.
There was another class of experiment which is in between, which is something which is more complicated than GCD. But you notice an algorithm that's kind of really not, it's sufficiently complicated, it's not totally clear. Something similar, which, again, if you think the solution and everything comes up in GCDs, something that also involves GCD. And that study questions like how to do representation and that how long it does.
So these one involve for many of the answers, these one involves GCDs. Yeah. So one thing else one wants to do is like go to the data and remove the ones that could be answered via GCD.
Yeah, I would move all the ones where the failure was divisible by 2 starters.
Again, there's much more data to do.
No, in that spirit, like you already know from the answer you've been this one, right? Like is a paper, paper dust doesn't follow. Exactly, we're trying to compare different models for that. Makes sense to just try running some experiments.
That was why I said.
Yeah, but it's one for torsion, there would be no failures. They would all satisfy the principle for torsion at low lysogeny. But yeah, there are other things one could try to do in genus 1 that would be of a similar spirit. But I'm not sure the large language model really cares so much about that. I'm
We're talking about transformer.
Sorry, we're talking about a transformer now. I'm not. Yeah, anyway, I find it intriguing. Yeah, it's like I've got some new scrub on the team who has some weird specialized skill that is able to outperform something that I've spent a lot of time thinking about, and I'd like to understand why. It's probably picking. My guess is it's not doing anything close to trying to implement the algorithm that might in principle work. It's seeing something else in the data that once we find it, maybe it will be obvious to us, but I also think it could be a spurious thing, I mean, we should.
Sure, and I think, it's like, there's some ways that half of the data. All of us will have gotten the answer correctly by doing GCD. So the first question, like, if you remove that data from the set, does it still give you some insight? Because now we're saying like it's doing better than him, but I think it depends on what set. With other sets, it does not do better than him because he knows the answer. It's an easy GCD computation. And other ones, it's hard and you don't know what to do. So there's all these questions about, and we need to.
But my suggestion for this week would be to urge people not to get too sucked down the rabbit hole on a particular problem, which I know, at least for me, is a very natural thing to do, because we have a limited amount of time this week, and I think the thing that we could get the most value out of is learning how to use these tools, trying to think a little bit outside the box, running experiments, and getting some, some sense of what might work, what are things we should be trying, and how to work with these tools. I mean, obviously, it'd be great if some, mathematical discovery was made this week, but I don't think it should be the priority, and I think it's more important to, explore this new world as broadly as you can, and hope to take away with you things that you can then, drill down to your heart's content on a particular problem.
So you'll still make up a list of problems.
Yeah, so that's what we're gonna move to next, but actually, before I did that, since Jim is here, I might be misremembering. Did you give a presentation on generative adversarial networks? Were you involved in that project, or am I misremembering?
Not in this context. I wrote one damn paper on something very different years ago.
Because this was the one other, this is going back to a workshop there just like a few days here at CMSA, I think almost 2 years ago now. But one other thought I've had in my mind for a while that I've never really been able to realize was there have been a number of successful machine learning projects that have basically involved teaching the model to play a game. And so there's a couple of different ways of doing this, but there are a lot of search algorithms where you can structure it as you're searching some landscape and you have a finite set of a discrete set of moves you can make at any given point. And you're trying to you're just trying to train the model to be good.
Yeah. So if that's what you mean, then absolutely.
Okay, yes, so my question would be, now we're here, I haven't seen you in a while.
Good to see you again.
Yeah, good to see you again. So are there off the shelf tools or packages that I haven't mentioned, that could be explored, where we could explore this sort of game playing approach, whether it's single player or adversarial, multiplayer?
Yeah, absolutely. So this is a number of people in the context of this. There is a package that I like called Chainer RL that has a bunch of baked in reinforcement learning algorithms. Maybe there's more up to date ones.
I was going to say, yeah, that's been updated for a few years, as we discovered the other day. I don't know if it's being updated at all anymore, so it may not be the best one to use.
About 4 years old.
Yeah,
Yes, it is definitely old. The question is whether something has supplanted it that has.
Yeah, the most famous one is probably stable baselines, but I don't know. Yeah.
But this is very important though.
Can I ask one of you to post on Zulip?
Yeah, I'm happy.
Yeah, that would be awesome, because I feel like it's been in the back of my mind for a long time, and it's another option we might want to.
Give me an example of a game.
So I think almost any gradient descent search could be turned into a game where yeah, so like here's I'll propose a problem. So we have a large database of modular curves. And one of the things that we would like to understand about it, this is a question one could ask about in any curve. For modular curves in particular, we're often very interested in knowing what is the ganality of the curve, the minimal degree of a map to P1. Because bounds on the ganality give us bounds on other things, and will tell us whether we can get low degree points on the curve over what extension. And so computing the ganality of a curve is a hard problem. However, for modular curves, there are some things that help, because there's lots of maps between modular curves, and also there are transformations, modular functions that you can plug in that tend to do surprisingly well at improving the model. So one sort of really stupid way to get an upper bound on the ganality is to take your horrible equation that your computer spits out, which is usually what you'll start with. Like say I'm thinking like a model for x1 and n, where n is like, I don't know, 33 or something. It's gonna be, you're gonna get some singular model that's gonna be an equation in two variables with, a couple hundred terms, and the coefficients might be, 4 or 5 digits. So you might think it's, how on earth would you go searching for a better model? Well, one thing you could do is say, I'm gonna give you 8 moves. What are your 8 moves? Well, you can replace x by x plus 1 or x minus 1. You can swap variables. You can replace with x with 1 over x. And you basically come up with generators for Mobius transformations and maybe a few other things you might want to throw in there. And then you could okay, so now you have a set of moves. But if you wanted to think about this as a local search, a very naive local search would be just take the move that improves the equation in the best way possible. Now you have to come up with a good metric for what you mean by improvement. You shouldn't expect you're going to reduce the gonality. But so gonality would be what's the minimum of the whole of degree in any particular variable. You're trying to get that down. You can't always do that in one step. But what you might do is get the number of terms smaller, the coefficients smaller. You might simplify the equation some way. So you have some metric that is telling you whether your model is better than the one you had before. And so you could then say, all right, now you have your 8 moves. If there's any direction that improves your model, go in the direction that improves it the best, and just keep doing that. But you'll very quickly get caught in a valley. And so then you can say, I'm gonna let you look out, do like an 7 or 8 move look ahead is about what's practical, and then pick the best move within a given radius. But then it turned out the best approach was a simulated annealing approach, where we threw in some randomness so that it had ability to jump out of values. And the randomness is a temperature variable that you decrease over time. And at the end of the day, we ended up finding, not just getting improved gonality bounds that improved on the best that were known at the time, but also finding some standard transformations that sort of like almost always worked, and actually could give you an asymptotic bound on like when n is divisible by 4. If you apply this transformation to sort of there's a standard way to construct a model for x1 or 4n, then you get a much better model out of it. And so that was a useful outcome, was that we learned some transformations that were sort of common. And I think that part of it was very specific to the fact that we were working with modular curves, not just random modular curves, but modular curves are very specific. But I think in general, you could print almost any sort of optimization, algorithm where you might have thought you were going to apply gradient descent. If the number of moves is possible moves, there's a small finite set that generates everything. You can turn that into a game. And your score is the lowest point you find in the landscape. That's just what's solid. I'm sorry?
Yeah, that's solid too.
Yeah, this is a 1-player game. Another optimization game though that I could imagine, I think I mentioned this when I talked to or I was trying to generate L functions that satisfy the functional equation. And I think there are ways to turn that in, so one player is picking the next AP, and another player is trying to come up with the worst test function that will make you, that will prove that you've done a bad job at extending your L function. It can't possibly be the L function, an L function that lies in the cellular class. And so then you could train these two models against each other. One is trying to find better weightings, and another is trying to get better at predicting the next AP.
Yeah, so as Jim said, we used this our other approach as a single player game for problem in number theory and solving dimensional equation used in knot theory or in group theory to find solve the shortest growth problem. And so these are the 1-player games that we have played with. Gabby is online, so he uses reinforcement learning as an asynchronous 2-player game. So essentially 2 players, but it was unbalanced, and it was very, very similar to what we just said. You have 2 players, but one tries to optimize, and the other one tries necessarily. So there's a lot of expertise. People are interested in this. There's certainly there's previous work that this has been implemented successfully, and I will post the link to the when I post the link to the package that we use.
That would be great.
Even for improving the modular curves equations, one could think more basically grammar basics. In the end, most times they don't care about grammar basics, they just care about some basis that's much better than what you started with.
Yeah.
So trying to figure out a way to go from ideal generators that are horrible to ideal generators that are nice. So
yeah, actually, that's a good example of a problem where there is an in principle of algorithm, but it's totally exponential.
And if you can prove every step, you don't care if you're running the grammar-based algorithm or not. You just care that your thing is because usually when you're running grammar-based, you see like the computers are adding more things. You see your ideal growing and growing and growing. You never know if it's gonna ever come down in this time of Earth. But if you have a way to shortcut take the tunnel of this mountain, then you'll win.
I think Mike Stillman tried something with personal basis.
But they was trying to. Okay, I will need to read more about that. But I think I remember the point was about switching the ordering along the way.
Yeah, I can't remember what you said.
Yeah, I know people have looked into this, but usually it's about like switching the Yes. What is the best order to like?
Just to amplify the point they were making, when you talk about such a general thing as growth bases, it could be that some particular source of problems, there are many things that, things that patterns of decision could be settled if we're not doing the general sense. So, just because the one that's putting on the base news comes up with something that's all, we have a totally different data set.
Sure, but Mike Stillman, he wrote this general purpose package for it.
Well, that's worth taking into account, but it's still the case that,
Yeah, I think that's a very good point. I think in general, we should not overinterpret, negative results that we're trying to solve a problem that's much more general than the problem we actually want to solve. I think that a Grosvenor basis problem in general is probably hopeless, but for a very specific family of varieties, it might be quite attractive. All right, I'm conscious of the time, so I want to start brainstorming projects. So sorry.
Can I just raise one logistical point? I did look at stable baselines a year or two ago. Maybe you guys know the answer. Okay, so like a lot of transformer libraries are bazookas and are hard to approach. Francois wrote something that is very approachable to many of us and like can get going pretty quickly. Is stable baselines a bazooka or is it approachable?
You attach
I'd say it's as complicated as it was for production.
Yeah. So
it's not that complicated.
It's not that complicated. There's more of a barrier than just downloading into it. But I mean, getting the channel out.
Yeah, exactly.
So
I guess what I'm asking is, would it be useful for someone who writes a wrapper for stable baselines that helps facilitate getting going?
I mean, it also contacts gym environment. That's
Yeah.
So if you want to hack deeper into it.
If you have a gym environment written there, you just literally attaching the two is not too hard.
Yeah. So you write the gym. It's the same as general.
Yeah.
Okay, good.
So the answer to that is always yes. I will tell you that the first week we spend more human hours managing that and figuring out how to do something instead of doing something. Because you're putting number theories, trying to learn all these 20 tools and like which one is to use right now, and we're always like doesn't work. So it's like in some ways for us, perhaps the end user, having something that's like might not be the best in the world, but it's like give me really like a bazooka, like I want something to put in, maybe not bazooka in the way you thought about it, but like I want like something simple, not perfect, but can run simple experiments.
Perhaps, yeah, exactly, and maybe not at the risk of pushing the analogy too far. We don't have military training, and Francois taught us how to use a bazooka. And so, like, if there's an ability to make it even easier, so yes, the number theorists are going to have to write their own gym environment because you're going to have to so on and so forth. But there are also stable baselines. There's a million different reinforcement learning algorithms in it. If there were a couple that were pre-selected as useful, I don't know whether it's PPL or HPC or something else these days, but I just think a wrapper that simplified the whole process for people would be very useful.
100%, and also a very good README file. I think that's one of the great things about Francois repo, and also I was very happy to see your README in your. Okay, why don't we move start thinking about problems. So there were a few that were posted on the Zulip. Do you want to pull those up right here? But I know that there were a lot more that were talked about and not posted on the Zulip. So your shy period is over. Now we need to step forward and actually suggest things. Yeah.
Okay. So there were two problems. There was the one by Terry. So again, it's on Zulip. Everyone's on Zulip. I hope you have read it. I think.
Yeah, I'm not going to try to explain this problem now, but I'd encourage people to take a look at the blog post, which sort of sets the context and suggests why Terry thinks. And the other reason why this might be interesting is they're going to publish within the next few months, I think, some results of this initial database. And so any improvements on some of these things would be, I think, would catch a lot of attention if the timing worked out. Oh, speaking of attention, I also wanted to mention that in the final workshop, which is, when is it, I think there will be an opportunity for presentations. So if anybody has, and you know, if I don't want to put any pressure on anybody, but if anybody at the end of this week, if people have results or something interesting they want to talk about, yeah, please let us know. Please let us know. We're looking for presentations. I think we have room for maybe 2 number theory presentations. Yeah, on the improving models, I'll post it now. There's a paper I can link to that has explains the algorithm that I used.
Okay, I'm just trying to type the things that you said out loud, but people should maybe I'll say that can I get an assistant? I think so. We should start to write the.
You want me to write on the board?
I think like you should keep getting projects instead of some people like you being done like. You shouldn't copy paste now the board, but you should try to get more projects on the board.
Okay.
Or I'm trying to.
You're putting projects on the board, right?
But I'm writing them. Therefore, someone should engage with the audience.
All right. So I think the guessing out functions would be an example of potentially an adversarial game that maybe it's worth. Yeah, and the improving models is like a heuristic search, which could be a single player game. The other 2, let me just get those out of the way that were on the blog. Or sorry, on the Zulip.
So these are welcome to the number theory channel.
Yeah, there was one by Kedlaya.
Proving lower bounds on place of totally real elements.
But it's positive.
Totally okay. Actually, yeah, you need totally positive. Okay, sorry.
The next one, do you want to say anything about this, Jen?
Sure, yeah. So I guess prior to last week, I knew of one example of an exceptional isomorphism between modular curves, the non-split Cartan curve level 13, the split Cartan curve level 13. But I think it's very interesting if there are more examples, and David Rowe, maybe Drew and some others computed using the modular curves database, a list of I think now several thousand examples, these exceptional isomorphisms. So it'd be good to try to use some machine learning tools to better understand this data set. And I think isomorphism testing in general is very difficult. And so this is done for genes 2 and 3 curves, but if we get some results, maybe we could better run this on genes curves.
I don't know how to write your name, but
You could imagine, right, like machine learning predicting good candidates to test.
Yeah.
So instead of having to sort of search
Sure, yeah.
everything.
So it has the group label, I guess, and so you know every modular curve is associated with a group, and so I don't exactly know the way this is structured, but there's some information about level and genus.
Yeah, I think just asking it to just giving it the equations would probably be. I mean, I think it would be more interesting if you could give it other invariants about the index change. Well, obviously, it's not be the same, but there are other invariants of the modular curve that could be included, where you might be able to ask it to try and identify pairs of isomorphic for non-obvious reasons.
okay, so adding the name to the end of the projects. Not that the people own these projects, but if the project not yet written down on Tulip, then they should try to write something down. And
why don't we put in the end-to-end project that you did with local torsion failure? Because I think it seems like there's agreement that investigating what's going on there would be a useful thing to do.
yes, but I was I think it's more the key part that these are the people that you can seek to get more details about the problem, or perhaps convince them to write on Zulip so that the problem is accessible to everyone. And there, I couldn't show.
Okay.
Yeah, so along the line with guessing our functions and internet, is that can we generate APs? Like, so 2 examples is that given like the first 100 and generate the next one using something like intuit. And another thing is that can we just give it a wild stress equation, and then theoretically that should be able to the APs and the intuit able to do that.
Yeah, we had something like that 2 weeks ago. Last time.
How about like just mod 2, mod 3 or something? Yeah, I mean, I think there might be ways to make this problem. But yeah, like maybe. So this seems really hard, but another, you could say, I'm going to tell you the first 100 traces of a mod 3 Galois representation, and I want you to tell me the next 100. And now the numbers are much smaller, and maybe you can do better.
I guess it didn't do very well.
What's that?
Implicitly, you seem to say she tried this a couple weeks ago, and it turns out the numbers were too bad or something, so it's bad.
Yeah, that's why I'm saying the model might help with the coefficient growth. It would still be impressive if we could do it even.
Right, it'd be great if we could do it again. Yeah, I was just making sure that.
Yeah, I think the experiment was we're trying to it did the curves, we're trying to guess it too, and the issue was with the I'm summarizing very roughly, but the issue was that our idea of is it good or not, it's not good was very rough. And so we had to so it was not really good for like some kind of gradient descent, because either you get it or not if completely, and it was hard to try to match the model. That's what I remember. That was the mission.
And were you running it to it, or were you doing
No, we're doing at first we just try to do like statistics.
Yeah, so I mean, I think the specific idea would be to use end-to-end, right?
Yeah, but Francois is on the call, and I hope Francois is going to correct me, but I lost whatever call is. Yeah, Francois is there. Hello, Francois. I think we'll need some help, like from Francois at some point, because I struggle with. As you see in my demo, Intuit will struggle a bit at some point. I struggle a bit with it, but at the moment, the thing I can do is binary classification. But I can see there's code behind the scenes to do more than that, but it requires modifying the code, and I was not ready to go like.
No, you could classify any group, it's always a classification because you're minimizing cross entropy, but you can have as many classes as you want. When I predict integers, it's like, as many classes as you have elements in your base. So if you're stuck on that, let's try to have a meeting, a one-on-one at any time you want, and I can show you how to do it.
Perfect. Yeah, I need to talk to you. I just the Google Cloud gave me enough pains of hours of pain this morning that nothing.
The general idea is that you have a vocabulary. You have a vocabulary for the encoder and a vocabulary for the decoder, which correspond to the base you are using. So there are as many tokens as digits in the base you are using. And the model is predicting separate tokens. So if you have a threefold classification, it's like predicting number in base 3, 1, 2, 3, etc. So there's no. Yeah, maybe there's a little few things to do in the environment. So yeah,
we'll talk.
Just ask me and I'll definitely help.
The Intuit, we need to modify it a bit, but it's been proven so far, at least for binary classification being very, very strong, which I think I will need to talk. Realize I'm not sharing screen, so I should do that.
Other projects.
Okay, so I have one. This actually goes back to Michael Stoll, who has stated this is a problem a few times. I think most recently in the MIT Mordell conference. And this is to do with finding curves of large hyperelliptic torsion packets. So what's going on is you take a curve of the genus, I'll keep it simple, 2 over Q, but the problem is actually over an algebraic closed field. You embed it into its Jacobian using geometric bias transport. And then you look at the intersection of the curve with the torsion on the Jacobian. And there was a conjecture of Manning and Mumford that this intersection should be finite, and then that was proved by Michel Feydeau for the first time. And there's now several proofs of this. And so there is a question of how large can this torsion packet be? So the geometric torsion on the curve. And Coleman looked at this in the 80s and thought that 22 would be the largest for a genus 2 curve. And subsequently Kuhnen wrote an algorithm in PariGP to actually compute it. So you input a genus 2 curve and it can tell you the size of this hyperelliptic torsion packet. And Michael Stoll ran this, I think in 2009, and found an example of like a torsion packet that was larger than what Coleman thought it would be, namely of size 34. And so Stoll framed this problem as find a genus 2 curve of larger torsion, it will prove that none exists. And I would like to use fun search to try this because the fun search rubric, as I understand it, also broke some record, found something larger, found a larger cap set. So can one use fun search to find a larger hyperelliptic torsion packet? And yeah, so that's the question that I would like to pose.
Yeah, that sounds very interesting, and that kind of raises a general question in my mind, is that the cap set problem, a lot of things we talk about for fun search, solution space has this combinatorial structure. And there's more choices, and there's some natural way to represent a curve. I think of like a defining equation.
Yeah, so it's very easy to write a curve is just a polynomial. That's quite
but that's, I would say, for the structure. Right, it's just got a few coefficients, or maybe say the modular reduction coefficients. But what would be a way to represent that it has combinatorial structure that you model can do it?
One way would be like model P, and it will tell it all the points that pass through model P for certain points. Obviously, this will be not very much information, but I don't know anything about torsion packets. But questions like this is much more combinatorial. You can think about finite field and say like, to what points does the curve pass through? But then we need to convert these torsion packets to something like that. Anyhow, problem to think about.
Yeah, that was always my guess, is that would much improve the quality of the funds.
And this is sort of where my question earlier was coming from about like, do we want to focus on Python? Well, so not do we want to, sorry, like, is that a limitation? Because that, like, I don't know if Python can compute like these torsion packets, but
But you can wrap it, you can just take all the stuff that, you feel with programming, and the outside, that's what I'm about to that's also just kind of cool.
I think the biggest challenge is figuring out what's the right way of encoding the problem. And like in the fun search with the cap set, the task of actually building the cap set, asking the Python program to write things, and putting them in, and then checking the cap set condition, all that's outside the scope of the Python code. That could be written in whatever language you want. And so if there's a way to encode information, somehow you want fun search to be producing some sequence of bits that you can then use, by calling it iteratively to turn it into a genus 2 curve with lots of torsion, or large torsion pattern. Other.
This is related to in some way, but for a genus 2 curve, the largest known example, so a curve with lots of rational points. It's an example due to Elkies and Stoll, and they found it by searching K3s, and slicing them various lines, and the record is 642 rational points. So GNOME shared with us a list of families, and so there's some way to gamify like this, slice and find good lines to then having candidates for lots of rational points. But I don't know about tools.
I like this idea because now there's some structure. You've got these families, and maybe the game is trying to find parameterization or a line through them or hyperlink through them where you can get, and maybe there's a way to encode that efficiently. Yeah, but I think this is a good example in general of throwing in some additional ingredients rather than just saying I want curves with lots of points. Saying, well, I think here's a region where I think they could be found. Here's a way to search efficiently, or to get around and get a way in those regions that you can somehow encode in a way that we try out. Other suggestions? Looking at a rule. So you've been thinking about these kinds of things for a while now. What would be your favorite problems?
So I should preface this saying I have very little intuition for what kind of things are amenable to this, but one problem should be nice is so if you have a cubic field, for example, and you want to understand the two torsion in its class group. Now, the thing is that you can express the two torsion in its class group as a cohomology group, and this cohomology group sits inside the same infinite cohomology group as certain cohomology groups of elliptic curves. So like but of course these are all infinite groups. You can't really do anything with that. But what you want to do is you want to find elliptic curves with small height if possible, which such that you can cover this class group with Selma groups. So it's something about covering a torsion subgroup of a class group of a number field with Selma groups of elliptic curves. And there are like obvious ways in which to do this, but they're not very good. And it might be that you can find clever twists which reduce the height and so on and so forth.
Okay, so then do you have a sense for, does this seem like an optimization problem to you, a search problem, or a game?
Like a search problem.
Is it like for a particular cubic field, you're then searching for the right elliptic curves to use?
Yeah. Like it's possible that there's a combinatorial pattern there that it's hard for humans to see, but that a computer might find.
Yeah, okay, yeah, let's.
I wrote it down, but you can correct it.
Yeah, I mean,
If I research something.
think about ways to parameterize the search, yeah. Other suggestions?
There's this very nice paper of Bhargava, Zhang, and Skinner, in which they prove that they really sort of push up the percentage of elliptic curves that can satisfy BSD. And they use a lot of sort of combinatorial tricks there, essentially trying to control the root number of elliptic curves. I mean, just I guess more generally, like you want to prove that you have lots of elliptic curves with both root number 1 and -1, and you can play twisting games sometimes to do this. Like you take a certain class of elliptic curves, you twist by something, and then you say that they must be. And that's also like a very much like a search problem. You're searching for good things to twist with, along with like a good class of congruence conditions to put on your family of elliptic curves, and hope that that will.
And is it easy to measure success? How do you?
Yeah, you can compute root numbers very quickly, so you should be able to.
So what's the goal? The goal is like you keep. I mean, what's the input? That's
Is the structure of this that there's like these various essentially lemmas that you could apply, and you're sort of trying to figure out how and where to apply them with what choices to.
Yeah,
Absolutely. So the input in some sense would be like congruence conditions to put on A and B along with a number to twist by. So it's not that many inputs to be perfectly honest. And then you want to see how well the root number is controlled by this.
And your goal is to get a particular root number, or you're trying to get a 50-50 split?
So I mean, every family that you make in which say root number 1 goes to root number -1 under the twist will increase your proportion of root number.
Okay, that's interesting.
Given that I'm the one writing I do not yet understand the problem. Input is. That's the thing I'm struggling with.
Yeah, sorry, so it's find congruent subfamilies of elliptic curves. So by that, I just mean you take a Weierstrass equation, you put congruence conditions on A and B.
And this is over Q, right?
Absolutely, absolutely.
Yep.
Along with a number n that you twist your elliptic curve by. So that, for example, root number 1 curves go to root number -1 curves under twisting in this family.
So that we understand.
You're trying to maximize the number of curves in the family that where the root number changes twist, right?
So the problem I'm having, and maybe you can just tell me to stop this.
I just mean in terms of the root number of the original curve. You just want a relation between the two root numbers.
Yeah, but I understand the other relation, but for us to gamify the problem or to understand that we're achieving the problem, we're achieving success or not. When I write understand, I do not know what I mean by understand.
Sorry, so what you want is for the root number of the twisted curve to be minus the root number of the original curve.
Okay.
For everything in that family, for everything in the congruence family.
For everything in the congruence family, but if you get it for a very high percentage, then
Yeah.
presumably there's a sub-congruence family.
Yeah, I think we should award getting close, right? Because then you can probably drill down.
Yeah, but what you're looking for the proof, to have a proof is a family where it's everything, because if that's true, then you would be able to just check it automatically.
Yeah.
But the way to maybe look for it is to score by how well you're doing.
So your score would be what, and you can approximate this by just trying a bunch in the family. Your score would be how often does the sign flip, what proportion of does the
I mean,
change sign?
because the percentage is empirical.
Yes, absolutely. In some.
I'm still having our anyhow. I'm going to move forward.
Yeah, we can talk. I think it's good.
Okay,
So is your plan to again go back?
Yes, I just want to make sure, we're getting tight on time. So are there any other projects people want to propose? We can do more projects tomorrow, whatever, yeah. And I also wanted to say so the next thing we're gonna do is we're gonna vote on problems and hopefully form a not too large number of groups for people to work on different problems. We have I guess G02 reserved for throughout the day for people to work, and there's also common area upstairs, and we're gonna meet. The plan is for this week is we want to meet every morning to have sort of a check-in on where things go, which projects are working, which aren't. Do we want to try something new, and also to talk about things. So, and we're going to try to start a bit earlier on Tuesday, Wednesday, and Thursday. So at 9:30 rather than 10:30, so that we have more time to actually get something done before lunch. Okay. Yeah. So
did we write anything else in our chat? I'm asking you, anyone that has access to it.
There was this thing about like sum of three cubes, but like 114 or something.
Yeah,
like that.
I don't.
Okay, that's not long. Okay, so basically now we're going to vote of approval. So the idea is that you're gonna raise your hand if you like. This is a worthwhile problem to work on. Doesn't mean that you will be happy to work on it, but doesn't mean that you're committed to this one. Does it make sense? You look lost.
Are we going to use that online tool again?
I was gonna go do it in Vim.
Okay.
Because the online tool requires me to ask the name of everyone, and you guys watch me again trying to type names, and I struggle with that. So I'll just vote with it. So improving constant in number theory, and now I need to stop sharing because I need to look at it on Zoom. Okay, this is so. Maybe people on Zoom, you can just shout out if you're interested. Maybe that's the best way. Otherwise, I cannot also share. Okay, so we would like to work on improving costs in linear materials. So the problem posed by Terence Tao. So we have 2 people. Again, you're just saying that you find a problem cool and you'll be excited to work on it.
So like last time, we're going through them twice.
Yes. So it's basically going to figure out what's our most popular problems, and we go from the bottom. So the most popular, like, do the 2 people that vote on this project really want to commit to this? There might be things like, like Phil's mail is there, so they might go like, yes, I'm going to work on this week. But so we're trying to just figure out popularity before people commit to a project. That's the idea. Improving models of model curves, heuristic search game theory. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Guessing L functions. 1, 2, 3, 4, 5, 6, 7. I should say that we can vote multiple times. We can vote on all of them. So again, we're trying to see like what are the most popular projects. Improving lower bounds on trace of totally positive elements. Kieran posted about this. 1, 2, 3, 4, 5, 6, 7. Exceptional isomorphism between modular curves. 2, 4, 5, 6. Okay. Investigation of local to global torsion. 1, 2, 3, 4, 5, 6, 7. And I think guessing other factors. I'll put myself again on that. 1, 2, 3, 4, 5, 6. Find pairs with the high record torsion packets. 1, 2, 3, 4, 5, 6, 7. Generic 2 curves of record large fractional points. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Find small height elliptic curve. Yeah. So what I will propose is the idea of finding small height elliptic curves that suggest that the sum of groups cover the class group of a certain cubic field. Count 4. Get a problem for rule. Finding congruent subscribe elliptic curves that we understand how the root number changes. That's how I understand the problem. 2. Okay. My sorting didn't go correctly, but not gonna worry about that.
I see.
Good enough. Right. Oh, I see. I sorted on the first character. It's okay. We'll survive. I'll bet it's the bubble sorts. Okay, so now the idea is that we're going to commit, and you're going to start from the bottom, and so there's some time that you will say like I'm going to work on this today, and again we're going to be tomorrow at 9, so it means that you might work on something today and be like this is pointless, there's nothing here to do or it's too complicated, and you might change. So you're not committing for anything more than today, but at least you're committing for today. So this will give an idea that there want like 2 is the minimum. Again, if 2 people really think that it's worth to stick to a problem today, it's fine. But we're trying to find like maybe 4 people. That would be the one ideal number size. So I'll start with the improving constants in linear theory by Terence Tao. Okay, so we're done with that. The subfamilies of elliptic curves. Does anyone commit to that today? Here, no one. Small height elliptic curves that explain the class group of a cubic field. Also not there, okay. Guessing other factors, maybe model. So engine, Coco, I don't know how to.
I'll go.
No, I'll go too. I know.
This is how you want me, okay. True. Okay, so. Did I miss anyone? No. Exceptional geometries between model curves. So I saw no one. I hope every time that I for improving our bounds on traces of totally positive real elements. Okay, and now you're gonna watch me butcher your name? No?
KYU. YU.
Y.
Y.
The W should be a Y.
That should be Y.
KH is fine. KH. KH. Okay.
Dyslexia, that's okay. Guessing out functions. I think this is very similar to the lower one, but I'm gonna.
Yeah, maybe we should combine these.
Yeah, I think last week we had sorry, last time we had this issue that there
I mean,
was.
the difference is whether we try end-to-end or guessing out functions, but I feel like maybe it's better to do them one at a time than one.
Yeah. I'll put my other things on my stuff there.
There too.
Anyone else would like to be added to the?
Since it's into int, I'm happy to help. Just ping me.
Great. Yeah.
Great. I'll need I'll need your help in many ways, but finding curves with I records large torsion packets. Don't want to commit to that today. I don't see anyone. Investigating local to global torsion.
Let's go now.
So improving models of model curves. We have a rule. The rule is alone.
Then maybe not.
That's okay. Did anyone say anything on Zoom? Oh no, I know there are people on Zoom, but they need to. I told them to shout out this. Okay.
I'm happy to switch to that team since there seems to be enough on the other.
Yeah, you can always switch around, just to be clear. True. You said, Ash, are you confirming that? Can you say out loud that you're confirming that joined this group? Okay, you're there, bye.
Thanks, Ash.
Okay. Genius 2 curves with record large personal points. My cuts will be hard. I'm missing someone. I don't know, you know.
Tom. Tom's fine.
Oh. Like that?
Yeah.
Did I miss anyone else? Okay, so these are our groups. I'm gonna post them on
I'll
Zoom.
switch it to the oil factors.
Yeah, so I'm gonna post this on Zulip so people know what are they good for today. It'll also help us with some ideas for tomorrow and so on. But again, you didn't solve everything today. The idea is to just get something started today. So let me do that right now. Oops, I don't want to last part. Did I have the chat for the other thing? I was trying to see if I wrote any last time.
Can I ask, Kit, are you gonna be around today if anyone needs help with one search?
Yeah, I probably be around a bit. I'm also available too.
What is your plan for the week?
I'll be here some days, but I'm not exactly sure which, definitely tomorrow.
I think there's a post session for content.
Yeah.
So
which if I mispronounced the name of anyone. They're there. Okay, and now my task is to give a simple demo of int-to-int.
Would it make, how are we for time? Like, do we need to?
There's no deadline. So I can take that.
So the demo is very simple. I was trying to follow Francois's. So I've done it before, and I was trying to follow something. So let me share the right thing.
Hide.
So first, I should first start like, do you have an account on this server? If you have an account, you can go to our Zulip, go to the message of the first week. The token is the same, so you can like. Let me just show you. When you sign up, we'll ask you for some example or some email. That asks for the token. So you need to put the token here to register. And that's how we kind of keep control of our resources.
And which Zulip topic has still been posted in?
Welcome.
Welcome.
The first
the welcome number theory.
Yes. Yeah. So before I go to the demo, I need to talk about more things. So now we have 8 GPUs, 8 like small GPUs, because my screen is too big. And there's, so I'm showing this why, because basically every time, most of the tools nowadays, they automatically pick your GPU, but most of the tools nowadays assume that you only have one GPU, call number 0. So it's important when you're running experiments that maybe before you start running something, you take a peek on the load, what's going on. Because if all of us run our experiments in GPU 0, so if I my screen is messed up. It's like there's a graph that you can see the load. We can look at the numbers. You can see there's only device 6 that has some load at the moment. And 7. That's me, most likely. But the point is that you should look at this before just by default running your experiments, because if everyone's running the same, then we all suffer equally the same. Because then the GPU business is telling everyone like, excuse me, like you're always like all trying to get to use a coffee machine at the same time.
How do you look at this?
Good point. Yeah, I type NV top. Someone should type that on Zoom. But you can ask me also again. Okay, so the demo. So first step should clone the repo. As you see, I really do not know how to type. And as Melanie was learning in the beginning, the code expects arrays of integers codified in some way. So by default, the base is 10,000. So I'll make this notebook public and or the whole project public, so you can do whatever you want with it. But the idea is that you need to basically write an integer in this base 10,000 with a sign plus or minus. So that's what I mean by this piece plus or minus, which is sign. And then you kind of this will be a number, which should be A1 times 10,000 plus A2. So that's my code that's here. For some reason, I also need to convert string of integers, a string representing an array of integers to an array of integers.
Is your notebook somewhere where people can see it?
Yes. Sorry, the fact that my resolution is quite. Oh, there's someone. Okay. Thank you, Brenda. So in this case, what I tried to do was to load the next part. Is that I loaded the data of the elliptic curves. It's important to load a small set. Or like you should try to run the experiments first on a small set, because otherwise you're going to spend 5 minutes decoding your data to realize that perhaps something went wrong. In this case, I should show you how to read one of the Bruce files. This data from first, I don't know, 2 million elliptic curves ordered by some order. I put the columns, I just read as a panda. Again, the notebook is available, and my guess here was let me go try to guess the rank. And as I told you, I struggled a bit to guess a positive number. Instead, I went for something more basic, which was trying to guess not if the rank, what was the value of the rank, but trying to guess if the rank was positive or zero. So now first I should look at the data set. I think that's another important thing is that I can see that even though I want to split between 0 and 1, it's kind of nicely split. Not everything is like 0, not everything is 1. If your data set is very skewed, you should filter it out to make it more balanced. Otherwise, your room to see your fitting of your is your model learning anything? Is just learning average or is learning something else? So then basically I use the snippets of code I gave you above to encode the integer array, which is basically the coefficient of your elliptic curves called A variance. That's an integer array I convert to a ring of integers. Then from ring of integers I encode them the way that Francois wants. And then for the rank, which is my output, I get basically asked is the rank positive or not? I convert it to an integer and convert that back to a string. So then I generate my lovely text file. And I already generated the text file, but now here I should again look at the count to be sure that I'm not doing something dumb. I can show you a lower example where I did something dumb. So here you see that there's I cannot count 2.3 times versus 1.2 million. It's okay. You can see some improvement. You can see if your data is getting there or not. It's about 60%. The next step is important, is shuffle your data. So I give you some bash commands to do that. Because when I put exclamation points, exclamation mark, it means that it's running this in the terminal. So just shuffling the data, making the data shuffling, then the file, then I just get the first 2 million to train, and I take 100K to test. Then for my own sanity, I check again that the data set it's balanced, test and a train, because it's very easy to make mistakes along the way. And now the magical thing, it's to run into it, is that you're going to give it this command. You don't need to do sage minus Python. You can do just Python, but then you need to install all the libraries, and you're gonna have trouble. So I recommend to run sage minus Python. And number of fork is the same, so you should use CPUs or not. Should put 0. Dump path is where you want all the logs to be dumped. And what's going to happen is that then you have experiment name. So basically, it tells you I'm going to put things in Scratch, and then my experiment name is it's called A variance to rank. And so it's going to make a folder with that file name, and then there's an ID, because the right way to do these experiments is that you not run one experiment and you overanalyze it, you do 10 experiments with different parameters and you see if what was the model is performing. And then you need to point out what the train data and the eval data, or what I call test data. So in my version of int-to-int, I modify it to also take option of local GPU. I'll make a PR to Francois' repo after we're done with this demo. But alternatively, there's a way to change your GPU inside of the code.
So what was num workers again? Is that?
It should be 0.
Yeah, put it at 0, 0 or 1. It's the number of workers for the data loader, and you usually need only 0 and 1. It checks that. Something you might want to add here is seed. So you might want to have, seed and put -1. No, put a negative number. The idea is that if you have a positive number or a 0 number, the system is deterministic, which is a good thing because you can redo it, but which is a dangerous thing because if you run it twice, you think it's 2 different experiments, but actually it's the same because it's seeded exactly the same. A negative seed will guarantee that the seed is random. So if you run twice the thing, you get different data. So your mileage may vary here, but you probably need to always state the seed to know what you're doing.
So by default, the seed is what? Is not by default the seed 1, -1?
I think the default is 0 or not.
You're right. Okay, so good point. Okay.
So it would be, so it's not seed, it's env-based seed, by the way, if you look at it.
So that's env-based.
Env-based seed. You might want to make the default -1, which would be a safer thing. Actually, PY. Yeah, that might be a better idea.
Yeah. Okay, so also, again, I said I added this parameter, local GPU 7. You'll be able to.
Is it possible to run on more than one GPU?
It is, but okay, so I'll answer your question in 5 seconds. So now I run this, and let me again do the NV top. Okay, 5 is empty, so I can do 5. And hopefully I did not mess up anything. And start running, and okay, it's going to take a while to load the data. Hopefully nothing fails. Fingers crossed. And now you can see device 5. It's not yet running anything. Sorry, it's kind of here. Okay, it's starting to run, and you can see that in a bit, device 5. Oh, I stopped NV top. That's why. You can see it's using like maybe 15%. Yeah, okay, see the number there, 15%. So, Francois can advise us how to use the GPU better. For example, can increase the batch size, but at the moment, the default parameters do not limit you. It's not the GPU size is not the issue. So I don't think the first thing is like, can I use more GPUs? I think the first thing should be like, how can first efficiently use one GPU better? Right. And I play with something like increasing batch size, but then you can see that does not fully improve the timing that much. So I do not know anything about this.
If you show your logs, Edgar, I can explain why. Can you show the logs? Yeah, you see here at number of parameters, you've got 4 million parameters in the encoder and 5.5 in the decoder. So altogether, you got 10 million free parameters. Assume 4 bytes per parameter, so that's 40 million. And you've got a GPU with 22 billion parameters. So it will take you a lot of work in order to fill the memory of one GPU with this. So you can increase the batch size. Yes, it will aggregate, but you will never fill the GPU. A 22 gig GPU is such a small model. That's just what I'm saying.
Okay, thank you.
So we basically have a DPUs or one GPU.
Yeah, I think this could work on on much smaller GPU. If you have a 6 GB GPU, this will run. But what you see is the numbers that we're moving. You see you're processing about 580, 590, or a little less than 600 examples per second. So if your epoch is by default is 300,000 examples, you can have a good estimate of the time you need to run one epoch to have evaluation, all that. The good thing here you can see is the arithmetic. So arithmetic is the loss, and you see it's going down, but now it's sort of stabilized. So you need to wait to see if it still goes down or not. You with me? But this is nicely running anyway.
Yeah, well, I think it'll take us a while to get to epoch.
How many epochs does one up to?
So there's a parenthesis say that so many, what's the max of epoch?
Okay.
I have
Yeah,
not
in
ever.
general, excuse me, in general, the way I run it is that you define a max. There's a number of there's the epoch size. Epoch size says how many examples you have in one epoch. It's up to you to choose it. By default, it's 300,000. You can reduce it if you want. At the end of every epoch, you got one evaluation on the test set. The max epoch, I usually make it very large and I just scale the process when I'm happy with the results. So I fetch the log all the time, look at the curves, and when it's done, I just stop it. But you could always reduce the number of epochs if you prefer.
So the thing, okay, we can let this run, but I think what I'm going to tell you, like I can jump to the feature, which I run this experiment. So Francois gives also a notebook to analyze the data. I modified the bit just by moving the things that we need to touch to the top. And if you run that, and I run it on this, previously I did not understand the folder structure, so it was a bit different. And then when you run all these lovely graphs that you can read the code to understand what the graph is doing, but you can see that the accuracy is quite stable. So basically the data set was 60% were ones and the rest was zeros, and after a couple of epochs, nothing changed. So in this case, like I don't see much learning going on there. And maybe one needs to let this run for a long time to see any progress, which I did not try. Because I was trying to get the demo that was give us something.
Do you have the train and test loss?
Yes.
Because the thing is that the train and test loss are XC loss here is very important. You will need to cap it to see what happens, because practically the accuracy usually doesn't go up at first. At first, you got a loss, a drop in your train loss, which is good, and you're supposed to see a drop in your test loss, which shows that you're not overfitting. So long the test loss goes down, there is hope. As soon as the test loss stops going down, probably nothing will ever happen. So XC loss is the thing you want to look at here.
Yeah, so I think so. I was busy. This my friend were busy playing around with the batch size and other things. I was not trying. My goal was not really try to see if I could learn something from this thing, because I think this one is quite hard. But the point here is that I give you an example of getting something binary. I tried to modify int to get something not binary, and I failed at it. So I'm just going to stop here. But I think one thing I want to be careful is that it's kind of really important to always look what you're doing. So I can tell you one example I was trying to do. I was trying to guess the sign of discriminant of the elliptic curve, which is a number which can be positive or negative. But looks like our data set always gives you the absolute value. So I was like, finally, was very happy something was running, and I look at the data set. It was like, I'm learning one. So it's I recommend you stop reading notebook when you get to CM. I have not run the CM experiment. I can try to do it now. So CM experiment is another field where I'm trying to get what's the if an elliptic curve is CM or CM, but my guess, and that's why I have not run the experiment yet, is that when you do this, you're going to see that the data is very skewed. So, because so skewed, I think it's going to be very hard to learn anything from it. But anyhow, I hope to give you at least here's some code to copy paste and run the binary classifier. I'll talk with Francois to generalize this. But in some ways, if you know what you're doing, the key part to generalize what you're doing binary is like this arithmetic folder file that tells you, depending on your experiment, how do we encode things. Like here's how to output the auto encode output and also auto input output. Sorry, auto encode out input. So we need, yeah. But I think I'll drop Francois to improve this library a bit.
All right. Thank you. Maybe we should, sorry, Melanie.
One small technical question. Did you say something like you made some modification to have this local GPU parameter?
Yes, I'll make a PR. I'll make a pull request to Francois once I'm out of this.
Okay, all right, so all right, great.
Yeah. It's a very small. Anyhow, I'll add it.
Any questions? Maybe we should thank Edgar.
Gar, I know what your problem is.
Wait, but one thing is that I made the change and I'm going to copy the change, and I think the key part for everyone is that for example, if you use storage,
Yeah.
I'm going to save you some time to try to learn how to do the thing. Is that you will do Zoom. Yeah, so this is the way that you pick what GPU your torch thing is going to run on.
Where you want to be. GPU ID.
You know.
That's why we can edit our Zula posts.
Yeah, first I'll talk to you in a bit.
Yeah, just a second, because it's very easy. You just need to change one parameter. There's a parameter called operation, changing to elliptic, and it will work.
I tried that.
It works. No?
It didn't work. There was, we'll talk about it.
Okay, let's be back. Yeah, sorry.
Thanks, Francois. Appreciate the help. Okay, why don't we wrap up for the morning and